Good afternoon. Dr. Brent Constantz is a serial Silicon Valley entrepreneur and the inventor on over 100 issued U.S. patents, with more currently pending. He was a consulting associate professor teaching biomineralization, carbonate sedimentology, mineralization of bone, and the role of cement in fracture management at Stanford University. In the 1980s, Constantz discovered the basic process used by corals to form their skeletons in his doctoral studies. He used this to develop modern biological bone cements, which are found in most orthopedic surgery operating rooms performing orthopedic surgery globally. In 2007, he launched his efforts to address climate change by creating a sequestered CO2 cement for the use in concrete that sequesters carbon dioxide using a method that is scalable and economically and technically sustainable. In 2012, he launched Blue Planet to make sequestered CO2 aggregate for concrete. A Fulbright scholar, Dr. Constantz has been awarded many grants from governments, has testified before both the U.S. Senate and the House of Representatives about solutions to climate change, and has won a number of awards and honors, and regularly contributes to philanthropic causes. Please welcome Dr. Constantz.
Thanks. Well, imagine if we had the ability to actually mitigate climate change and restore the carbon balance to Earth. And what I'm going to talk about is I think the construction industry probably has the largest lever that we have available to us. The largest lever we have available to us to actually do something. And I like to ask people where they think all the carbon is anyway. And we'll go over that. But what I'm going to tell you is I think since concrete is the most used construction material, it actually holds the greatest capability to sequester more carbon dioxide than any other avenue available to mankind for a whole number of reasons, which I'll go through. But let's start off and just say, well, where is all the carbon? And what we're looking at in these graphs are the main reservoirs of carbon on the planet. And a gigaton is 1 billion tons. So there's 1,000 millions in a billion. And to put it in perspective, if you take all the carbon sequestration that mankind's done over the last 40 years, we've got about 30 million tons. So in the atmosphere, in that top box, you can see the whole atmosphere contains 750 gigatons. That's 750 billion tons. And in all the efforts of mankind over the last 40 years, we've only sequestered 30 million tons. Okay? So essentially zero. So these big multi-billion-dollar government projects you hear about where they're injecting CO2 into the ground, they don't even have the most remotest chance of ever affecting climate change. If you look at the oceans, the surface of the ocean, 750 billion tons of carbon. If we look at all the rainforests and all the biota in the ocean, you've got a few hundred gigatons, the soils, the mantle. Then you get to the deep ocean, and there's almost 40,000 gigatons of carbon in the deep oceans. But then look in the lower right corner. Look at sedimentary rocks. There are over 50 million gigatons of carbon sitting in rock. And most of that is limestone. A little bit of it is coal and some other fossil fuels. But it's almost all limestone. So most of it is ancient coral reefs, ancient deep sea sediments like the White Cliffs of Dover. If you look at the Great Barrier Reef today, you're looking at about 100 gigatons of carbon that's actually sequestered in the Great Barrier Reef. That's where the limestone comes from. Limestone is the skeletal remains of marine organisms. And it's where almost all the carbon on the planet is today. Now I'm going to show you another slide, and it's going to show you the exchange between these different reservoirs. And on the right, you're going to see what all the fossil fuels have to contribute in a big red line. And you can see there's about 9 gigatons of carbon that are coming from sedimentary rocks, and that's mainly coal. That's the burning of coal. But most of that is actually limestone in the sedimentary rocks, and just a very small portion is the 5 billion tons of coal that are mined every year. So what sort of opportunity do we have? There's about 55 gigatons of rock mined globally every year. That's compared to the 9 gigatons of carbon coming from the burning of fossil fuels. And I'm sorry to throw around all these numbers, but we're currently paying for, mining, and consuming 55 billion tons of rock every year, and most of it, over 70% of it, is limestone. And if you remember from your freshman chemistry, limestone, which is calcium carbonate, has a molecular weight of 100. Carbon dioxide has a molecular weight of 44. So if I have a ton of limestone in front of me, I've got 440 kilograms of carbon dioxide that's now mineralized permanently in the crystalline state. So if I need to mine, say, 55 gigatons of rock every year to support the need for rock, and by the way, there's a global aggregate shortage and a global sand shortage, that would have about 25 gigatons of carbon dioxide in it. So there's the lever right there. That's the construction industry. Those 55 gigatons of rock are being used for construction, for concrete, asphalt, road base, all that thing. So it's sitting in the hands of the construction industry. And I'll show you how. What we're doing is we go to large source emitters of carbon dioxide, and we capture the carbon dioxide. We don't try and purify it or anything like that. We don't go through any of the energy-intensive methods that are usually used to purify CO2 so you can compress it and liquefy it and dispose of it underground. We just do what corals do out in the ocean. We interact it with water and make a carbonate solution and precipitate a calcium carbonate and have the ability to form it into very hard rocks. And I like to show people we make rocks out of it. And this one rock could hold most of the CO2 in this room, in this one rock. So it's a great place to store CO2, and it's also permanent. Most of the things we do to mitigate CO2 are going to release it at some point, like burning a biofuel, for example. Once it's mineralized in the rock, it's permanently mineralized. It's not going anywhere. So the reason we're focused on making sand and rock from the CO2 is it's actually one of the only reservoirs that can take the amount of CO2 that's actually needed to be taken to actually really make a difference and substantially address the entire problem. The IPCC says we need to do 10 billion tons a year by 2030 and 20 billion tons a year by 2050 if we have any chance of coming close to the Paris Accord. And this is really one of the only places you can do that. Process, we use those pumpkin-colored boxes are the 3 process steps. Gas absorption, we take any type of gas in, we pull the CO2 out. The carbonate mineralization is where we actually form rocks like the one I showed you. and then capture liquid reformation. That's an interesting aspect because I'm going to show you where we get our calcium. So we get all our carbonate of the calcium carbonate from CO2. We get the calcium from all kinds of materials we call geomass, and it's a word we copied from biomass. But it's any sort of mineralogic material. I'm going to show you one example of a plant we're building in San Francisco right now that uses returned and demolished concrete as its calcium source, which is something that's provided in every city in the world, anywhere you have. And I'll start there to show you what we do with concrete. The ecosystem for concrete, for old demolished concrete in any areas, it starts off being demolished or returned. It can be landfilled or reprocessed. Sometimes it'll go into minor concrete. We actually take it and we dissolve away all the calcium, the Portland cement part of it. And what we're left with is the original sand and gravel. And so a byproduct of our calcium extraction process, actually in the case where we're using concrete as our calcium source, like in San Francisco, is actually the ability to reuse all the sand and gravel that's in all the old concrete. And it's upcycled in a way that it's as good as virgin aggregate, so it's not treated like recycled concrete is, for example. So these are the two materials that we're producing at that plant. On the left, you can see the recycled, or the sequestered aggregate, and 44% of the mass of that aggregate is CO2, now in the crystalline state, permanently sequestered forever. On the right, that's a byproduct of dissolving concrete to get the calcium out so we can make the product on the left. And instead of throwing it in a hole, it turns out it's a major part of what people call the circular economy today. Most of the circular economy is concrete. It's the biggest part of any circular economy anywhere. And the ability to just reuse all the sand and gravel from all the demolished concrete instead of opening up new quarries and hauling this stuff is a side benefit that's really valuable. But when we get that calcium, the way we make these rocks out of it, we call it geomimetic process. It's not biomimetic, it's geomimetic. It's similar to the way white sands in the tropics form, for example, to make those limestones. We started really pouring a lot of carbon negative concrete about 3 years ago at San Francisco International Airport. They have an objective to make the whole airport carbon negative and at least carbon neutral. And we started using a new rating system for embedded carbon called the Carbon Star rating. It's sort of based off Energy Star, but instead of about energy efficiency, it's about embodied carbon in a material. And so there's an actual quantitative rating that can show up in the specification. So the city and county of San Francisco can specify a concrete in their specification that's carbon star 0, which would be carbon neutral. So this is, for example, what the spec looks like. They've actually called out a carbon negative concrete in their specification. And what's significant about that is it puts the power to mitigate CO2 in the hands of the specifiers, which are often governments. And if governments want to actually do something about climate change, they have a much stronger lever with their procurement power than they do with their power of taxation. And there's nothing wrong with the price on carbon and all that, but it largely hasn't worked, and most countries in the world will never have a price on carbon anyway. But every country in the world's buying rock. Even the poorest governments in the world have big projects, they're specifying rock, and they have that power of procurement. So it's something that can apply on a global basis. just so you know, the aggregate market is outpacing the numbers we thought. It's probably going to hit about 60 gigatons of rock by 2020 that's actually used. In the lower left, that's California. Those are 4 counties in California, and the brown colored bars are how much quarried rock's actually available, and the blue bars are how much rock is actually needed. And so what's happening on a global basis, and you got to remember 70-75% of concrete is just rock, right? On a global basis, there are fewer and fewer quarries, and the distance that we're moving rock is getting longer and longer to those quarries. But I remind you that humans put out about 35 billion tons of CO2 a year. And there's about, there's over 50 billion tons of rock mines. So this is really one of the only solutions that's within an order of magnitude of actually doing something about that. If you go to progressive localities like San Francisco, well, it's okay, it's skipping one of the slides, but almost everyone is pretty far behind in their goals to reach the Paris Accords. Well, here's an example from the San Francisco area. The Air Quality Management District has set these goals by 2050, which are in accordance with the Paris Accords, but it is very far behind. So if you take a microcosm like the San Francisco Bay Area where we're building our plant, I'm just going to show you exactly how it would work quantitatively and economically, and why this could happen in Toronto, for example. There's about 7 million, sorry about the imperial unit, cubic yards of concrete placed in the Bay Area every year. Our project there, it's called San Francisco Bay Aggregates, is going to be manufacturing this synthetic limestone aggregate. It has the potential to remove about 11 million tons of CO2 per year. And if replicated globally in 5,000 cities, just this one small plant could take out 5.5 billion tons of CO2 profitably. Just to put that in perspective, if you look at everything the Department of Energy has done in the history, it's spent billions of dollars. They've done 16 million tons over 20 years. This big Chevron field off Western Australia is hoping to do 4 million tons a year. It's the biggest project in the world. So if we're going to be realistic, we have to come up with a real solution. So specifically in the Bay Area, if you look at the quarries that are available to us, we have permitted reserves in the North Bay of about 100 million tons. The 50-year demand's about 500 million tons, and Facebook's building a new campus, Google just built one, Apple just built a new campus. These are huge, huge concrete projects. In the South Bay, it's the same way. We bring a significant amount of our rock from British Columbia. But we're actually going to be producing it just right up in the North Bay, along with this recycled rock, shutting down the distances, but also sequestering a lot of CO2. And this is a map of where all the concrete ready-mix plants are. There's a lot of them within 20 miles of our plant, which is labeled their SFBA, and 30 miles. So the way this works in a place like California, which is the 5th largest economy in the world, is we bring in 240 million tons of rock a year into the state. And our transport distances are up to 200 miles on average to bring the rock. Caltrans spends about $5 billion a year bringing that rock in. That's our State Department of Transportation. It has a $12.5 billion budget. A lot of it's coming from British Columbia. Only 34% of the quarries needed are actually permitted anyway. So if we were to say to California, look, let's make all that limestone right here in the state out of our CO2, it would take 105 million tons of CO2 to make that much limestone. And we have plenty of refineries, cement plants, power plants, even direct air capture ways to get that CO2. And we actually have laws that require us to get down to 400 million tons by 2020, which we're going to do, and 300 million tons by 2030. So just by replacing the rock with limestone made in California, we could meet our 2030 objective and do it profitably without spending any more money than we're already spending. It's the same cost. It's just instead of digging it out of the ground and transporting it, you're making it out of CO2 locally. So that's our approach, and we think it has the legs to actually be propagated around the world. We're working on other plants right now with large cement companies, steel mills. The plant we're at in San Francisco is at a natural gas-fired power plant, which supplies most of the electricity of the city and county of San Francisco and puts out almost 2 million tons of CO2 a year. But it has tremendous applicability. For example, in China, we were discussing earlier how China has poured more concrete in the last 3 years than the US did in 100 years. Well, China is an enormous contributor to global CO2 emissions. And, you know, what I wanted to communicate is where this is available, the more concrete you use, the more carbon negative your building's becoming. And to couple with energy efficiency, imagine if every building, because of its concrete, started off with a carbon bank account. What we can do, for example, is a typical cubic meter of concrete has about 200 kilograms of Portland cement in it. So it has a carbon star rating. It's got a carbon footprint of about 200 kilograms. But if I take the sand in that and I replace it with our limestone, and I take the gravel in that and I replace it with our limestone, I can bring that cubic meter of concrete down to negative 1,000 kilograms. So instead of your carbon footprint being huge because of your concrete, it becomes dramatically negative. And then the way you think about using concrete changes completely if what you were trying to do is having a carbon neutral or a carbon negative. And that the whole idea is that the built environment becomes where we're going to store all the CO2 permanently and safely. Thank you.
All right. Did we have any questions? Can I ask you to step up to the microphone there? And we're going to limit it to 2. We need to get our speaker to a plane. So.
Thank you. I appreciate that.
Okay. Well, I'm not convinced by what you say. As I understand correctly, you're arguing that by replacing the silicate rocks in cement or concrete with limestone, you're creating a negative, carbon negative concrete.
No, it's not. It can replace geologic limestone or granite, it doesn't matter. You're taking CO2 that would have gone into the atmosphere, and you're capturing it before it goes into the atmosphere, turning it into limestone. So
okay,
it doesn't.
well, here's the problem. When limestone forms naturally, it is sequestering carbon, but it's also a source of carbon dioxide to the atmosphere at the same time. Because what happens is like 90% of the dissolved carbon in seawater is as bicarbonate.
Bicarbonate, yeah,
Yes.
I know, I teach a class about
And you
that.
know
So,
bicarbonate gets
two
converted into
bicarbonates
a carbonate
plus
and a
calcium go to
CO2, and the
CO2
CO2
plus
goes into
calcium
the
carbonate,
atmosphere.
yeah.
So
That's
it's
not
actually...
that's not what we're doing, though.
Okay, so yeah, the key is really where the calcium comes from, because what happens with natural limestone is you're reducing the alkalinity of the seawater, and that makes it a source of CO2.
Right.
So really, I think the whole key to whether your system really is carbon negative, and I'm not yet convinced, is where that calcium comes from. You mentioned some geomimetic material.
No, we're talking about return concrete. So we take return concrete, it's dissolved,
Okay.
and it releases ionic calcium. It also has alkalinity, so we're not doing 2 bicarbs plus a calcium go to CO2 plus water plus calcium carbonate. We're doing carbonate plus calcium go to calcium carbonate. So we're not producing any CO2.
Okay.
We only have time for one more. I'm sorry.
Yeah.
I'm really curious about how you're like the capture part of this, the equation. So what industries are you thinking of like capturing from? Is it like a scrubber? How expensive is that technology on the capture side?
Right, it's not like an amine scrubber like you'd see in traditional CCS. We use gas liquid contactors. We use an ammoniated solution. We create an ammonium carbonate solution. We can use a variety of contactors, but right now we use something called a liquid cell made by 3M, which has a very high surface area. It allows you to interact this solution and form that carbonate right away. So something that's unique about what we're doing is we don't incur a high cost or a high parasitic load capturing the CO2. So like a natural gas plant is about 5% CO2 in the exhaust where we're working in San Francisco. We just convert it into carbonate rather than trying to purify it. Anytime you're working with purified CO2, you've sort of lost the battle before you started, because just the process of capturing it, purifying it, and liquefying it has such a large parasitic load that it's not really worth it. We don't incur any of that because we just convert it at the same concentration to carbonate, and then we precipitate the calcium carbonate.
All right. Thank you. Can we mention your contact information for